Bismillahirrahmanirrahim. Hello everybody. Today we are going to solve this exercise. So we have to prove that the supremum of a is equal to the square root of 2. How we can deal with this kind of questions? We suppose, or we suppose that we don't know. Let supremum of a be equal to a real number. A is greater than 0 and a square is less than 2, so a is near the square root of 2. We can suppose that a is greater than, well, the supremum greater than 1. This is not necessarily, but just a remark. We would like to prove that 2 is less than or equal to a plus 1 over n square and greater than or equal to a minus 1 over n square. If this is true for all n greater than 1, this will give us that the supremum of a, which is equal to a, is equal to the square root of 2. We aim to prove this double inequality. We will start by the simple one, this one. This one. What we can say? What we can say? We have supremum of a is equal to a. By the characterization technique, characterization of the supremum, for all epsilon greater than 0, there exists an element x epsilon from a such that what? Such that a minus epsilon is strictly less than x epsilon, and this is less than or equal a. This is true for all epsilon, any given real positive number. If we take epsilon equal to 1 or over n for n greater than 1, this is still true. Why? Because this is more general than if we take a special case. If we take epsilon equal to 1 over n, there exists an element x and xn from a rational such that a minus 1 over n is less than x and xn from a less than a. This is positive because we said that a is greater than 1, and this is less than 2, less than or equal to. This is less than or equal to. So this inequality is true, and it is verified by using the characterization of the supremum. Let us deal with this one. This one. We suppose by contradiction that this is not true. Suppose that this is not true. This means 1. This means what? This means that 2 less than or equal strictly greater than a plus 1 over n square for any n greater than 1. This is the by contradiction. In more suitable form, 1 over n square less than 2 for all n greater than 1. If a is rational number, a plus 1 over n belongs to q, a is less than, which is less than 2, so square. Here we have a problem. This means that we have a rational number which verifies this inequality and is greater than the supremum. Contradiction, this is not possible. So if a is rational, this cannot be true, because we have a contradiction with the supremum character of a. We have a rational which is greater than the supremum, so we have a problem. This is not true. The second case, in the case where a is irrational number. So suppose that a is irrational number. In this case, what do we have? We have a. This is less than what? This is less than n plus 1. A, we take the integer part over plus 1 over n plus 1, and this is less than a plus 1 over n, and this we will call this one, call this one w. We have a square less than w square less than a plus 1 over n square, which is less than 2. But this one belongs to q. So this one belongs to q and is greater than a, which is in q. We have a problem. What is the problem? This is an element from a which is greater than a. So this cannot be the supremum. We have a contradiction if we take square with, and why this is greater than a? Why this is greater than a? Because n plus 1 a, if we take the integer part, this is less than n plus 1 a, or equal. This is less than or equal to n plus a. And this one is strictly greater than n plus 1 a minus 1. If we take over n plus 1, we take here over n plus 1, this is equal to a. If we take here over n plus 1, we simplify this with this, so we keep a minus 1 over n plus 1. A minus 1 over n plus 1. If we add plus 1 over n plus 1 here and plus 1 over n plus 1 here, 1 over n plus 1 here, we will cancel this one and we will have this rational number which is greater than a and less than a plus 1 over n plus 1. If we take the square, this will be less than 2. We have a contradiction for this reason. Conclusion, this cannot be true. So the opposite is true. Finally, we prove that for all n greater than or equal to 1, we have 2 less than a plus 1 over n square greater than or equal to a minus 1 over n square for all n greater than or equal 1. It can be equal to 1. There is no problem. So we take this one first. We will get a square minus 2a over n plus 1 over n square less than or equal to 2. This plus something is less than 2, which implies that a square minus 2a over n is less than 2, because if plus something which is positive is less than 2, if we cancel this, it remains less than 2. Here we have a square minus 2, this one, less than 2a over n. We divide by 2a, we let here 1. A square minus 2, this is positive, 1n goes to plus infinity. This will be a square minus 2 less than or equal 0. This means that this first from this one. From this one, we repeat the same thing and we will get a square greater than 2. A square greater than 2, a square less than or equal to 2. This means that a square is equal to 2. This means that a is equal to the square root of 2. We take the positive number because we are in the positive part. This is the first method. I will give you second method. The second method for the second method, we consider sequence which is equal to n square root of 2 over n for n greater than or equal to n. This square root belongs to a and it is non-decreasing. This one is non-decreasing, and you n converges to the square root of 2. So the supremum of a is equal to the square root of 2. Why? Because the square root of 2 is a point of the closure of a, the adherence of a. This is a second method, but we can consider it for answering differently about the first question. How we can show that this is very easy? We can use just the characterization of the integer part of a real number. This is the square root is a real number, but if we take the integer part, it will be in it will be in Q. This is a second method, a very short answer about the second method. Thank you very much. See you next time.